Hello everyone, I'm Zhu Wang from University of Waterloo. Today I'm going to show you how we can build an RFID transmission line to detect finger inputs. Human-computer interaction is a hot topic because we are now surrounded by more and more smart devices like smart TV, smart locker, and so on. Traditionally, we can use smartphones, voice assistant, or camera to control those smart devices. However, they have multiple limitations. For example, the smartphones are not easy to share. The voice assistant is not convenient in your workspace, and so on. Camera has privacy issues. Recently, many research studies propose to use RFIDs for detecting user inputs due to the advantage of RFID technology. For example, the passive RFID tags are battery-free and cheap. They are also lightweight and wireless. Thus, the RFID tags are easy to share and embedded into common objectives to enable sensing and interactions. Although a lot of RFID-based UI systems have been proposed, they are not ready for practical applications. I will use this figure to summarize their limitations. In this figure, the x-axis is the robustness of a system to the changes of the input device location, and the y-axis shows the number of input gestures a system can detect. IDSense is an early RFID-based UI system. By training the RSS values, it can detect a limit of 5 inputs. To increase the number of gestures, real system uses the fine-grained face information. However, both the two systems suffer large errors when there are changes in the device location or the RF environment. To solve the robustness issue, paper ID and tip type use the ID information of tags to detect finger inputs, which is robust, but they have a limited number of gestures. Ideally, we want a system that is not only robust, but also enable multiple input gestures. That is our goal. To achieve this goal, in this paper, we introduce an RFID transmission line-based finger input system. Our system has 3 advantages. First, it is low-cost and battery-free, since we use the cheap commodity RFID tags. Second, our system is robust to changes in the device location or the RF environment. Third, our system achieves more than 95% accuracy, even when the input device moves over 48 locations. Since our solution is using RFID, let me show you how RFID works. Here is an RFID tag. It has an RFID chip and an antenna. The tag has no battery, so it requires a reader to transmit a high-power signal to power up the tag. The tag then can communicate with the reader by reflecting or non-reflecting the reader's signal. For example, the reflection means the 1 bit, and the non-reflection means the 0 bit. When the reader receives the text signal, the reader not only decodes the text ID, but also estimates the received signal strength RSS and phase. RSS and phase are related to the tag-to-reader distance, RF environment, and the test antenna. Now that I have explained RFIDs to you, we want to learn if we can use RSS and phase to enable a robust finger input detection when the location of the input device changes. To do so, following the existing work, We measure the RSS and face when a finger touches different positions on an RFID tag. In those two figures, the x-axis is the 7 touch positions on the RFID tag, and a baseline when there is no touch on the tag. Unlike existing studies, they locate the tag at a fixed location. We move the tag over 12 locations and measure the face and RSS at each location. Here are the results. The error bar shows the maximum and minimum RSS or face values measured at each finger touch position across the 12 tag locations. As we can see, there are significant RSS and face variations across the tag locations at any given finger touch position. Those variations introduce a big challenge because when there are face or RSS changes, we don't know the changes come from the finger touches or the tag location changes. So what can we do? Our solution is using an RFID transmission line to build a new finger input device. Let me show you. It's very simple and only takes 3 steps. First, we place 2 RFID tags in parallel with a separation of half wavelengths. Second, we connect the chips of the 2 tags with 2 wires. The 2 wires allow the transmission lines given the 900 MHz RFID signal. Lastly, we secure all components on a subtract. Now you get a new input device. It can sense the finger inputs when a finger slides along the transmission line. But let me show you how even this simple device can be robust to the location changes. We collect the RSS readings of the finger touches when our input device is located at 12 different locations. In these 2 figures, it shows the RSS of tag 1 and tag 2, where their x-axis is the finger touch positions and the y-axis is the RSS. Here are the results. Each line shows the RSS of one device location. We had 2 observations. First, the increasing or decreasing pattern of RSS across finger touch positions is independent of the device location. For example, for the tag 1, when the finger moves from the position 0 to 5, the RSS values of all device locations increase. When the finger moves from the position 5 to 14, all RSS radius decrease. The second observation is that the touch position when RSS peaks is independent of device location. For example, tag 1 and tag 2 always have their maximum RSS at the position 5 and position 11, respectively. Motivated by the 2 observations, we define 3 sections along the transmission line. Specifically, in this figure, A and D are 2 endpoints of the transmission line. B and C are 2 positions where RSS peaks. Then we define 10 different finger sliding gestures, where each one is done by sliding a finger along a specific section of the transmission line. For example, the gesture AB means a finger slides from A to B. The gesture ABC means a finger slides from A to B and to C. To detect the 10 finger gestures, we identify 4 single features. The first feature is the increase or decrease trend of the RSS. For example, the gesture input AB has an increased RSS trend for the two tags. The second feature is the relative RSS between two tags. For example, in this figure, the RSS of tag 1 is always larger than the RSS of tag 2. The third feature is the number of peaks. We calculate the derivative of the RSS measurements. We found that some gestures have two peaks, such as the gesture BC shown at here, while some other gestures only have one peak. The last feature is the index offset between the maximum RSS and the peak. We found that for some input gestures, the maximum RSS and the peak happen at the same time with a zero offset, but some are not and have an offset. We summarize the 4 features for all the 10 input gestures in this table. Based on the 4 features, we introduce a decision tree classifier to detect the 10 gestures. Our detection algorithm has 4 steps. Step 1, we use a peak feature to separate the gestures BC, CB, and the rest gestures. Step 2, we use the offset feature to decide whether the gesture is one of the AB, CD, or one of the ABC, DBC. Step 3, we use the relative RSS feature to refine the classification. Lastly, we use the RSS trend feature to distinguish two gestures that share section boundaries. Now let me show you the evaluation. We implement our system with a commodity RFID reader and tags. The system is tested in 2 environments, a laboratory area covered by 1 radar antenna and a classroom area covered by 4 radar antennas. In the first experiment, we evaluate the detecting accuracy when the location of the input device changes. In the 2 figures, the x-axis is the true input gestures and the y-axis is the detected gesture. As we can see, in both environments, our system achieves more than 90% accuracy to detect 10 finger input gestures across different device locations. In the second experiment, we test the robustness of our system to the environmental changes. When multiple people move around the experimental setup. In this figure, the x-axis is the number of moving people, and the y-axis is the precision and recall. Here is the results. As we can see, both the precision and recall are higher than 90%, even with 3 moving people. It implies that the environmental variation does not have a great impact on our system. Lastly, we evaluate how finger sliding speeds affect the detection accuracy, because different users may slide their fingers at different speeds. In this figure, the x-axis shows the 3 finger slide speeds: slow, medium, and fast. The y-axis shows the precision and recall. As we can see, both the precision and recall are higher than the 90% accuracy for all the 3 sliding speeds. But the accuracy decreases when the sliding speed is very fast. In this case, by increasing the reading rate, we believe the accuracy can be increased. Now, let me conclude this talk. First, we introduce an RFID-based finger input sensing system that is robust to the device location changes using a transmission line. Second, we introduce a finger input detection algorithm, which can differentiate gestures accurately. Thank you, and I'm ready to take questions.